This video chapter focuses on biocohesive rocks, Dunham classified as boundstones. In Dunham's original 1962 classification, he defined boundstones as carbonate rocks showing signs of being bound together during deposition. The signs of binding are quite specific within the sample that we're classifying. Components that are bound together in the original depositional environment by framework organisms such as corals, encrusting organisms, coralline algae, bryozoans, or by sediment-trapping organisms such as we see in stromatolites, where we see biocohesiveness related to cyanobacterial, all have this common characteristic in Dunham's classification of being boundstones. They can have quite complex internal structures. Biocohesive rocks show things like cellular detail, layering contrary to gravity, geopetal infill of voids, lamination with quite steep slopes, as we see in a lot of microbial bindstones, all indicative of the rock holding together as it's growing and accumulating. There's a typical coralgal boundstone, nice tropical rock, where the corals and the coralline algae are binding the rock together to form a wave-resistive reef framework. We see in situ associations of coral heads in growth position. Quite often we get plastic sediment captured in between the coral heads, and we'll come back to this notion of sediment mosaics a little later. Boundstones show components that were bound together during deposition. That's very general. In a study of the Devonian reefs in outcrop and also in the subsurface in the Great Canadian Sedimentary Basin, Embry and Klovan published a key paper back in 1971 where they further subdivided Dunham's classification. They added terms for boundstone broken down into three parts, where we had the original organisms in growth position to form a rigid wave-resistive structure called a framestone, coralgal framestone, as I just showed you in that previous image. We can have organisms encrusting and binding together, as we see in stromatolites, or we can have organisms acting as bafflestones, as we see in modern-day seagrass banks. The third classification is much more difficult to look at in the subsurface because quite often the organic components, the seagrass leaves, rot away during early diagenesis. Those three groups, bafflestone, bindstone and framestone, are subdivisions of Dunham's original term, boundstone. Embry and Klovan also added two terms for sediments which have coarser material where the grains are mechanically deposited. These are mechanically reworked components. So these are organic components that were not bound together. These are the debris aprons around a lot of framestone reefs. We see it in the Devonian, we see it in the modern. They're characterized by more than 10% of the grain components being coarser than sand size, coarser than 2 millimeters. If they're matrix supported, they're floatstones. If they're class-to-class supported, where the components are coarser than sand sized, we call them rudstones. Embry and Klovan designed it because they saw what was an insufficiency when describing reefs and reef-derived coarser-grained aprons across the rock records. So it's a combination of Embry and Klovan's classification and Dunham's classification we used to classify ancient carbonate sediments. The beauty of all these terms is that we can take them from the Holocene into the ancient and back as a series of analog modelling exercises. So if we've got a rudstone, the question we're always asking is, are the coarser than sand size components in class-to-class contact? Here's an example of a Inoceramus, a bivalve rudstone from the Cretaceous. These Inoceramus were quite impressive. These fragments are quite large. There's one of these shells from Greenland. We'll talk about these in a bit more detail in the next module, looking at geological aspects. This particular example of Inoceramus didn't grow and associated with a reef. It grew in waxstone and packstone conditions, but still, because these fragments broke down, they're in class-to-class contact, we have a rudstone. Here's an example of a Jurassic calcareous sponge-algal mudstone from the High Atlas. Once again, coarser than sand-sized material. That's a 1 millimeter scale bar. This is another example of a rudstone. Here we have a floatstone where we have the coarser than sand-sized components floating within a micritic matrix. This is a skeletal floatstone with micritic matrix, less than 10% grains, but those grains are coarser than sand size. Here's another example. This is a foraminiferal orbitulinid floatstone with a packstone matrix. Floatstone and rudstone are designed to classify the coarser components that weren't captured in Dunham's original classification. They also divided Boundstones into bafflestone, bindstone, and framestone. A framestone is where we have organisms building a wave-resistive or rigid framework structure where the, let's say in this case, coral heads are still in growth position. So we have in place large fossils cemented together into a supporting matrix. There's an example of a modern-day coral framestone, a scleractinian framestone. In the interstices, we can accumulate mud, or we can accumulate sand, or we can accumulate intrakarst debris. There's a whole range of sediments that will form in amongst those in situ coral heads. His core, through what is a heavily bio-eroded framestone from Hawaii. CT image on the left, a core image on the right. Here's an example looking down on a bedding plane of a rugose coral framestone from the Entolophyllum group of rugose corals in the Silurian, and the lower image is showing us a sponge crinoid framestone. Here's another framestone. This is a Miocene bryozoan serpulinid reef from somewhat deeper water. Then on the right we have an in situ set of tabular corals from the Silurian of Gotstone. In all of these examples, that framestone is in growth position as a rigid structure with various styles of sediment and cement in between those in situ frames. We'll come back to this when we look at reefs in a lot more detail in the next module. Here are bindstones. These are organisms that encrust and bind. These are the shark bay stromatolites. Here's an example of a stromatolitic bindstone from the Neoproterozoic. Here's an example of a bindstone in the process of formation where you can see the pink staining, the cyanobacterial filaments capturing those mud-sized fragments. And on the right we have a thrombolytic bindstone from the tidal channels in Lee Stocking Island in the Bahamas. We'll talk about all of these in the geological models we develop in the next module. Here are some Lake Clifton thrombolites in Western Australia looking down onto the thrombolite reef. These are bindstones because we have blue-green algae in here doing the binding. In this case, we look down on an individual dome. We zero in on the layering and we see the cyanobacterial mucus in those layers. And then here we see the final deposit with this clotted texture. This is a thrombolytic texture, an automacritic texture if you like. These are all examples of bindstones where layers are binding together as biocohesive layers to form a laminar, or in the case of thrombolites, a relatively structureless clotted accumulation. Then we have bafflestone. Then we have typically stalked in-place organisms trapping and binding sediment interstitially. So the frame's not necessarily cemented. The frame may not be cemented one to the other. It's the baffling effect that's capturing sediment in between those upward growing stalks and fronds. Here's an example of an upper Devonian bafflestone in the Canning Basin, where we've got Stachyoides stromatoporoids surrounded by Rhenausis, a calcium microbe, which we'll talk about in detail in the next module, with the remaining pore space capturing fine-grained micritic sediment. So here we've got fine-grained sediment accumulating in what was a relatively high-energy condition on the seafloor, where the baffling was done by Stachyoides twig-like stromatoporoids. Here's an example of a bafflestone bank in Florida where we're accumulating waxstones in between the seagrass fronds. A lot of the coarser material in the sediments in between the seagrass fronds, as we'll see in the next module, is coming from the epibionts living on the surface of those seagrass fronds. On the right, we have an Ordovician example of a crinoid bryozoal bafflestone. The bryozoans still in place. Here's another example of a bryozoan bafflestone from the Cretaceous. These are all examples where we've had baffling effects. Bafflestone, bindstone, and framestone are all subdivisions of Dunham's original classification of Boundstone. Have other classifications we can use to focus in on the nature of Boundstones. Here's Insalaco's classification of Boundstones. He still uses Embry and Klovan's terms for allochthonous sediment, floatstone, and rudstone. Then he divides framestone associations on the nature of the in situ shapes of the various calcareous skeletons. So we can have plate stones where we have horizontal platy to tabular skeletons with the height ratios between 5:1 and 30:1. We can have horizontal platy to lamellar skeletons, sheet stones, with a width to height ratio of greater than 30:1. We can have dome stones where we have domal to irregular massive skeletons. We can have pillar stones where we have skeletons with vertical growth attributes, tubular and branch. And then we can have mixed stones where no skeletal form dominates. So this is Insalaco's modification of Embry and Klovan's terms and Dunham's terms. You use the classification which is most useful for the rocks you're studying with the view to understanding those boxes of classification, giving you information about the depositional and the diagenetic environment. All carbonates are what we call mosaic sedimentation. Certainly where we've got framestone, boundstones involved, we'll see mosaics as we see here. This is from the Tutaki Lagoon in the Cook Islands, where we have patch reefs with granular sediment accumulating in between. We don't see this laterally transitional sediment type going from a boundstone into a mechanically deposited sediment in siliciclastics, where we're looking at energy levels on the bottom. Here we have wave-resistive structures, which could be partially breaking down to form mechanical accumulations. Sediment mosaics in carbonates are biogenic accumulations, typically where the grains are located at or near where it first forms, but we get these patchy patterns, both horizontally and vertically, that don't follow the predictable linear grain size gradients or the energy responses we see in siliciclastics. This leads to the notion of the reef wall, where we can have a variety of detrital fills in amongst the framework, along with a variety of cements. We can think of the framework as the bricks in the wall, the detrital fill, the sediment contributors, the breakdown products of the various corals, coralline algae forming the aggregate in the wall, then the cement holding those bricks together. We can have varying combinations of the biogenic cements, as in modern-day reefs dominated by the coralline algae, versus the precipitative cements such as aragonite and magnesian calcite that we see in many marine sediments. This also leads into the bucket principle, which I'll talk about when we get into sequence stratigraphic concepts in carbonates, where we can describe a coral reef as a bucket rim, or the rigid reef rim acting as an edge of a bucket which is trapping sediment. That reef rim is protecting the interior, but the system also depends on waves and currents to sweep excess sediment out of the way, either back into the lagoon or down into the deeper water settings, so that living framework, the bucket edge, the bucket top if you like, can continue to grow. This leads into concepts in sequence stratigraphy indicative of responses to changes in sea level versus growth rates of the organisms that make up the bucket rim. Finally, to finish off this general discussion of the reef, let's consider environments where we have mixed carbonate siliciclastic sediments, where we have in proximity terrigenous or land-derived materials coming up against our carbonate factory. This tends to happen in places like inner to outer shelf mixing zones, where siliciclastic sediments are prevailing in the nearshore environments, while further offshore we get our carbonates. And then we get a zone in between those two, as we see here with the siliciclastic shoreline and the offshore reef, a zone in between those two where we get a mixing of siliciclastic and carbonate sediments. We can also see it on tropical and volcanic island lagoons, where the rainfall brings out the detrital sediment off the volcanic islands, as we see in New Caledonia. Offshore, further away from those detrital input areas, we see corals dominating. We can also see it in lacustrine environments. In landlocked rift basins in Lake Nakuru in Kenya, we have a siliciclastic rim and a more carbonate-dominated centre. We also get ocean currents carrying fine-grained siliciclastic mud in the deeper offshore basins, where it mixes with pelagic carbonate sediment. Here's Mount's very simple classification of siliciclastic carbonate mixed environments, where the end members are siliciclastic sand in a tetrahedron on one axis. On the other is the carbonate alchems. Then we have micrite and siliciclastic mud. And depending on the varying proportion of those four components, we classify in general terms our carbonate sediment.